Good morning, everyone. Welcome to this week's AEROMMA seminar. It's my pleasure to introduce our speaker, Dr. Brad Pierce, sitting in the front row. Dr. Brad Pierce is the director of the University of Wisconsin-Madison Space Science and Engineering Center. He's also a professor in the Atmospheric and Oceanic Sciences Department. He received his PhD and Master of Science from UW-Madison in meteorology and was a physical scientist at NOAA within the Advanced Satellite Product Branch on the UW-Madison campus. Prior to NOAA, he was a senior research scientist within the Division of Atmospheric Sciences at NASA Langley. He has more than 30 years of experience in global and regional atmospheric composition modeling, data simulation, and forecasting support for airborne field campaigns studying the chemistry of the atmosphere, and this includes studies of stratospheric ozone loss and tropospheric pollution. In 2017, he led the Lake Michigan Ozone Study, which was a collaborative multi-agency field studies of ozone chemistry and meteorology along the Wisconsin-Illinois Lake Michigan shoreline using a combination of aircraft, ground-based, and ship-based measurements. In today's talk, he will talk about WRF-Chem tempo indirect validation efforts during AEROMMA and STAQS. And now I will leave the floor to Dr. Pierce.
So thank you so much for that nice introduction. As you said, I've done lots of field campaigns. I have to say that this campaign last summer was probably one of the highlights of the campaigns that I've been on. And that's because, first of all, we finally got NASA NOAA aircraft to fly over the Midwest, which they had not done before, except for partially during the 2017 ELMWAS campaign. But more importantly, we were doing science under tempo. And so this tempo is something that a lot of people, including people here, have spent a long time trying to develop, and now it's in orbit and we're getting measurements. I'm gonna be talking about some validation efforts that we were doing during last summer. I'd like to, first of all, acknowledge my two students, Gerald Octon and Maggie Bruckner. Both were in the field supporting flight planning with our forecast. Gerald was actually here in 2022, where he worked with Gabby Pfister in developing the WRF-Chem modeling system that we used for real-time forecasting, and now I'm using for this evaluation. So the last summer was quite a collection of field campaigns. Unfortunately, Gotham was one of the ones that was supposed to go. It didn't go, but it's gonna go next summer, which is good to hear. That'll be science under tempo as well. The ones that I'm gonna focus on are the NOAA AEROMMA, which stands for Atmospheric Emissions and Reactions Observed from Megacities to Marines campaign. And then there's also the NOAA CUPIDS campaign. I'm not gonna talk about that, but it was at the same time. And then the NASA Synergistic Tempo Air Quality Science Mission. So I'm focusing, these campaigns started out out of California. We're doing a lot of marine science. I'm not gonna talk about that at all. Then there was an eastern phase where they were sampling Chicago, Toronto a couple times, and New York City. And I'll be focusing on that period exclusively, since that's where we set up our modeling domains. They went back and did urban sampling in the LA Basin. I won't be discussing that during this presentation. So again, AGES was the first science that has been done under tempo, and we were able to bring together all sorts of airborne and ground assets to really complement the tempo satellite to do science in urban environments, but also to use for validating those tempo measurements. So the AEROMMA, the STAQS campaign was all the flights were part of tempo validation. They're remote sensing instruments. The AEROMMA campaign had a number of spirals that were designed over specific ground sites to contribute to tempo validation. Tempo, it's a really unique situation now between NASA and NOAA, where tempo is a demonstration of now a future operational geostationary atmospheric composition instrument, which will be flown sort of in the 2032, 2034 timeframe. And that's part of the GeoXO constellation. So for the first time at NOAA, there'll not only be an operational goes east and goes west, but there'll be a central one. That central one will include, for the first time, a hyperspectral infrared sounder and an atmospheric composition measurement, which is a UV-vis spectrometer, very much like TEMPO. And so not only does TEMPO provide now proxy data to begin developing capabilities so that we can use the GeoXO composition measurements on day one, but it also allows the whole community to build up capacity. So validation of TEMPO and using TEMPO for future GeoXO missions is a very unique situation to be in. I think it hasn't been since the EOS satellites more than 30 years ago, 25 years ago, where NASA was doing development that then became operations. So I'm not going to go through this in great detail, but this is the outline from the TEMPO validation plan. And this is an example of the validation plan for NO2. So we're following the same kind of validation stages as was done for the Advanced Baseline Imager for GOES-R. We have a beta, provisional, and a full validation. TEMPO version 3 was released on May 20th of this year. It's publicly available, and it's currently at beta validation. We've got 3 different milestones that, again, I won't go into that are required for beta validation. Provisional validation really just extends the same beta validation analysis for 2 seasons, and provisional then is done for at least a full year cycle. So with the beta validation, we're actually in pretty good shape. Still issues that need to be sorted out, and I'll try and discuss some of those. But want to keep in mind that these are the kind of objectives that the validation is focusing on. So what I'm going to talk about today is indirect validation. Chemical transport models can play an important role in the satellite validation because they can include non-coincident measurements in the validation process. So for example, the DC-8 did spirals, over specific sites on specific days in Chicago and in New York. And those spirals are being used for TEMPO validation. But that's a limited number of spirals. GCAS did raster patterns that it's an airborne simulator for TEMPO, and so it was measuring the same kind of columns that TEMPO measures, but again, it only had a few flights. With the model, we are simulating what TEMPO sees all the time, and we can use the measurements, all the measurements, not just the measurements, for example, the DC-8 spirals, but all the DC-8 measurements to characterize our biases and uncertainties in the model. We can then compare the CTM to the satellite measurements to determine those biases, and then by just simple differencing of those biases, we can get an indirect estimate of how the satellite compares to the satellite for all the observation time compares to the validation measurements. So the approach, again, we use the AEROMMA DC-8 in situ NO2. I will talk about formaldehyde as well. That wasn't in the abstract. And then the GCAS NO2 measurements to evaluate high-resolution WRF-Chem simulations during August. In terms of flights, we've got 4 flight days in Chicago, 3 in New York, and 2 in Toronto. We can then, we characterize the fidelity of our WRF-Chem simulation, then we can compare the WRF-Chem simulations to TEMPO, and we're using the newly released version 3 over the same regions where we've characterized our uncertainties, but now we can do it for twice as many or more than that days. So Chicago 11 days, New York City and Toronto, and now we can look at time variation between 12Z and 23Z, and I've defined some latitude and longitude boxes here that will be the focus of where we're doing this validation. So, as is often the case, nature throws some surprises at you during field campaigns. I was involved in the in the 2019 Fire XAQ campaign where we were trying to chase fire plumes, and it was a very low fire year. One of the objectives was to get wildfire smoke interacting with urban plumes. For AEROMMA STAQS, the objective was sampling urban VOCs, hopefully in the absence of smoke. Well, we got lots of smoke. So 2023 Canadian wildfire season was the largest on record, more than double the previous record. It was associated with extremely warm and dry periods, and it's clear, at least to Environment Canada, that climate change contributed to these high record temperatures and dry conditions. I know I hear fires mentioned almost every time I'm talking with people here at AECOM, and we all know that fires are going to become a really big issue as we move towards the future. Anyway, these were the fires that were going on the 22nd of July, and you can see fires beginning in the western and the eastern Canada. This is now data from the VIIRS aerosol optical depth on the left, and OMI total column carbon monoxide on the right on the same day. And you can see that those fires smoke both in aerosol optical depth and carbon monoxide as a trace gas of these biomass burning. You can see that was beginning to enter the northern tier states of the Midwest. And if we look now 2 days later, this is from Aerosol Watch. This is the GOES ABI true color imagery with the surface PM 2.5 levels on the bottom. You can see that smoke came in over the Midwest and significantly impact surface PM 2.5 concentrations. So one of the things that we had to deal with within our retrospective regional modeling was dealing with the impact of this wildfire smoke. So in the real time, we were bringing in boundary conditions from either RACMs, which is my model, or WACM, and we kind of started with WACM, transitioned to RACMs, but in this retrospective runs, we went back. We're using WACM exclusively, and Gerald worked on tuning the Canadian wildfire emissions so that he got better agreement with some of the surface monitors in Canada. WACM by itself significantly underestimated the impact of smoke. So we've got enhanced lateral bound conditions, and this has largely improved the representation of Canadian wildfire influences. Our retrospective runs also had significantly more vertical levels below 2 kilometers. This is because one of the aircraft was Sea Ray, flown by Mike Newchurch out of University of Alabama, Huntsville. And his measurements of NO2 showed that much of the NO2 enhancement and variability was actually below our lowest WRF model level. And so we had to add 4 or 5 layers so that we were resolving things in this 5 to 10 to 15 meters above the lake surface. So now we're going to get to the first part of the indirect validation, which is comparison between WRF-Chem and all the aircraft measurements during the whole campaign. This is for the DC-8. The DC-8 flight tracks are shown on the left, colored by the days of the flights, and a scatter plot on a log-log plot is shown here. You can see we have a good correlation of 0.57. This is with the full the 1 second data, the model mapped to the actual measurements. Overall normalized mean bias of minus 10%, a slight low bias. And the majority of the data sits within the plus or minus 25 to 50% variation about the true measurements. So that characterizes the measurements from the DC-8. Again, the DC-8 has a ceiling of 1,000 feet, and so it can't get down very near the surface. You look at the peak of this, you look at the peak of the distribution, it's somewhere around 0.2 or 0.3 or 0.4 parts per billion by volume. This is data now from the Sea Ray. On the left-hand side is the map. Sea Ray just flew out of Chicago, and it flew always very near the shoreline and always very low. This is an example on on August 2nd, which was the Tempo first light. And if you look at that curtain, the altitude starts at 200 meters. That's above sea level. The lake is at 180 meters. So we're looking at variation in the lowest 40 or 50 meters that are huge. And you can see that it's doing sampling very near the surface, and then it goes out and does some sampling, again, maybe at like 300 or so meters above the surface. And that's where we see all this variance. This is an example where we do capture kind of the overall structure, but you can see there's a lot of fine scale structure that the aircraft is seeing that we're missing. And that's what gives rise to this RMS error. But we are capturing the mean features quite well. We didn't do that until we added a number of different layers below the model. So this one, we have a normalized mean bias of 20%, still pretty good, considering that this is an area that has quite a bit of variability. Correlation is slightly lower. But here you'll see, toggling back and forth, the mean observed and modeled NO2 concentration is significantly higher in these lower levels. So from a Tempo NO2 column retrieval perspective, much of the variance and much of the concentration is in this very lowest layer of the atmosphere, and that's a challenge. So the other instrument that we used, that's used for tempo validation and for our model verification, is the Geostationary Coastal Air Pollution Events, GeoCape, airborne simulator called GCAS. GeoCape was a NASA decadal survey project that, again, many people from AECOM were involved in, and it was to design a geostationary atmospheric composition measurement. Tempo is a realization of a part of that, and GeoXO, with both the UV-Vis plus the hyperspectral infrared, is full realization of the GeoCape plan. So again, to me, that's very exciting. So it's a remote sensing instrument, very similar to Tempo. Push broom, it does a swath width of about 45 degrees, and it scans 4 times per second. There's actually 2 different spectrometers on there. One is for ocean color. I'm not talking about that. Anyway, so it's a ultraviolet one at 0.6 nanometer resolution to retrieve NO2, ozone, and formaldehyde. So on the left-hand side, we have the STAQS flights. You can only see 3 flights on here. That's because they did the same pattern every time they're in the city. So it's flight pattern over New York and Long Island Sound, a flight pattern that covered Toronto, and then a flight pattern that covered the Chicago and the Western Shore of Lake Michigan. And then this is the comparison combining all those measurements together with WRF-Chem. And here you can see we have a very high correlation and a remarkably low bias. Normalized mean bias is 2% compared to these measurements. And here, what I'm doing in these is GCAS provided, the GCAS NO2 retrieval provides air mass factors that are both based on GeoCF, which is the GMAO global model that is used for the Tempo air mass factor, and they provide a retrieval that uses our WRF-Chem model as the air mass factor. So this is a comparison using GCAS and my model using the a priori information from my model.
Right.
Yeah.
What are all these points sticking out to the left?
Those are, so I didn't filter, those are very low measurements from GCAS that are, you know, I don't, they're well below the detection limit of the instrument. And, you know, I don't know where those very, very low concentrations come from.
Looks great overall.
Yeah, yeah. Those are, this is a log density plot, so those outliers, you know, I'm trying to show all the data, and people have actually, I was on a call with Laura Judd, who made these measurements. She said, all my plots show scatter outside of my plot boundary, but, you know, the data's there, so. But those are very low, and those could be, you know, those could be kind of indication of the noise floor of the instrument. Okay, so here's some examples of comparisons between, on the top, GCAS, and on the bottom, WRF-Chem, where I'm using the WRF-Chem for both of these, I'm using the WRF-Chem air mass factors. And you can see the kind of patterns that they flew. This is for Chicago on the first light, for Toronto 2 days later, and then New York City on the 9th. And you can see, generally good agreement. There are differences, but this is the kind of data that we're then using to verify the model. So we saw a very, very good agreement when we combined all the measurements together. We want to look for regional differences in the tempo retrieval because of different albedos and things like that. So for this analysis, we've now broken up the GCAS data and the comparison with the model to Chicago, Toronto, and New York City. And now we can see that biases we're getting some compensating errors with the model showing a low bias over Chicago, a high bias over Toronto, and a kind of a medium bias over there. So now we've characterized those biases and RMS errors in these specific areas that we're going to do tempo validation in. So the tempo data for the actual baseline product, the validation is it's co-adding 2 tempo pixels for NO2, and actually for formaldehyde, it's co-adding 2 tempo pixels and co-adding 3 different hourly measurements. So, because formaldehyde is a much more difficult gas to retrieve. What I'm doing in the subsequent analysis is just doing that co-adding of neighboring pixels. So all the results you'll see here are applying a boxcar averaging. There is certainly some pixel variation in the tempo data that the tempo science team is looking into. So here's the same days, except now we've got tempo on the top and WRF-Chem on the bottom. And now in this case, I am using the same air mass factor that the tempo retrieval uses. So this is using the GMAO GEOS chemistry forecast air mass factor, which is a 25-kilometer resolution model. And in here, I've defined 3 different boxes. This is the box that I'm going to focus on validation, indirect validation for Chicago. This is the box for Toronto, and this is the box for New York City. And again, on this particular day, you can see patterns are generally similar. You can see that the WRF-Chem on this day shows a much higher plume up along the western shore of Lake Michigan. It's also showing a higher plume in the urban core here than tempo. And here's the results now, similar to the GCAS results, except now it's WRF-Chem versus tempo. So I'm going to spend some time on this slide. So again, this is for Chicago. High correlations for all 3. Biases now, the model is systematically higher than tempo for all 3 of these sites, and that higher model result is larger than the result for GCAS. You can also see that for these highest NO2 columns, particularly in Chicago, and to some extent in New York, the model shows higher values than tempo did. That wasn't the case for the GCAS comparison. So with these biases, we can now take the difference between the model minus the observations for GCAS and the model minus the observations for tempo, and then we can do indirect validation for all the tempo data that we were able to look at in August of 2023. That results for Chicago a low bias of tempo relative to GCAS of about 13 times 10 to the 14th, -9 and -10. So again, this is 10 to the 14th. This, typically I look at NO2 columns in kind of 1 to 20 times 10 to the 15th. And so these are fractions, these are down at very low, these are down here at the low end of the distribution of these observations. So this is very, very good agreement. So again, high correlations, biases are they're higher than compared with GCAS, but as a result, you see this overall low bias relative to GCAS. And the RMS error ranges from 22 to 28 times 10 to the 14th versus 19 to 30. So very similar RMS errors, and we can attribute a lot of that to the model not being able to capture some of this fine scale structure. Part of that is also due to residual noise in the tempo retrieval. Now I'm going to switch over to formaldehyde. So this is the same. We don't have GCAS formaldehyde retrievals yet, so we can't do as thorough of a indirect validation. But we do have DC8 in situ measures from Glenn Wolf. Again, we get a very high correlation, but we have a high bias. This high bias, basically this is the free troposphere with no formaldehyde, and this is the boundary layer with where all the formaldehyde is, and we have a high bias. But we do capture the boundary layer structure, the boundary layer transition of formaldehyde very good. So again, we characterize that it's well correlated, but we've got a high bias of about 40%. This is the same thing now as before, except it's for formaldehyde. On the top panel is tempo, on the bottom is WRF-Chem, the same different boxes, and you can see that the formaldehyde is noisier than the NO2. But this is a single tempo formaldehyde retrieval. Anyone that's worked with, for example, OMI formaldehyde retrievals or tropomi formaldehyde retrievals, you typically have to average weeks or a month of data on a fairly coarse grid before you can knock down the noise. So the noise level for this formaldehyde retrieval, to be able to look at a single pixel formaldehyde retrieval is pretty remarkable, and that's a testament to the spectral calibration of the tempo instrument. Anyway, so we're doing the same thing. You can generally see patterns that are similar. Formaldehyde has quite a bit less variation than NO2. You can see from the model, most of the formaldehyde signatures are probably biogenic kind of VOC signatures at this time and at these latitudes. These are the statistics, just like we did before, except now we're not comparing with GCAS. We're comparing, this is the comparison of the model to tempo directly. We don't have a comparison with the GCAS. What we can say is that the biases between the model and tempo are very similar to the biases we see with the in situ data, about a 17 to 38% high bias in the model, 38% for the DC8. The RMS range for these measurements is actually well below the precision requirement for the tempo formaldehyde retrieval, and that's a precision requirement when you co-add not just 2 pixels, but you co-add 3 different hours of data. We're co-adding 2 pixels, but we're looking at a single swath. So that again, these are remarkable results. Look forward to be able to kind of close the loop on this with the GCAS formaldehyde retrievals. So I've got conclusions here. Looks like I'm well ahead of time, so that's good. We've used indirect validation to extend our ability to look at more of the tempo data over New York City, Chicago, and Toronto. First, comparing the WRF-Chem, we have low normalized mean biases relative to DC8, slightly larger relative to the C-ray, and very low relative to the GCAS column measurements. And from here, we can infer biases between tempo and GCAS that range from a low bias of 9 to minus 13 times 10 to the 14th. So these are small negative biases. In terms of the RMSE, again with the spatially averaged tempo NO2 retrievals, the range is well within what we found for WRF-Chem and GCAS, and so we can attribute a lot of that to just inability of the model to capture some of these fine scale features. And then for formaldehyde, same kind of result. We have a normalized mean bias that's consistent with the DC8 data, and we'll finalize the analysis when we have the GCAS NO2. So I won't go through the rest of that. Because I have time, and in the abstract I did say I was going to talk about diurnal variation, I'll move on to that. So another one of the objectives of the tempo NO2 validation plan is to look at diurnal variations in urban and rural regions. So you remember those 3 boxes I defined over Chicago, New York, and Toronto? Within those, we subset those boxes to an urban area, Chicago or New York. We didn't do it for Toronto. And then a neighboring suburban area. So for Chicago, it was the western suburbs, and for New York City, it was Connecticut. So obviously, like for example, in New York City, a lot of times Connecticut gets the New York City plume. So the difference is this is not a true urban versus rural comparison, but it is, can we capture gradients that reflect this urban, suburban kind of gradients that we would anticipate? So what we do is within these regions, we've got all these co-located WRF-Chem comparisons, 86 granules in Chicago, 89 in New York City, and then we composite that data in this box, in these 2 sub-boxes, an urban and a rural sub-box, and composite that into hourly means for August 2023. For this one, quality control is the highest quality control. Cloud fraction has to be less than or equal to 0.15, and I'll try and touch on that a little bit towards the end. That's a very low cloud fraction, lower than typically used for the polar orbiters. And in here, I'm excluding all the negative tempo retrievals. So this is a time series, and the reason I put these as extra slides is I'm still trying to sort out what this analysis means. I was talking to Dave Edwards and Sarah a little bit about it earlier. So the black line is the tempo, hourly averaged data. On the top is the respective urban area. On the bottom is the respective suburban area. I've put the means over the whole time period in there. The black is the time series of the tempo data with plus or minus 1 standard deviation. The light blue is our WRF-Chem model with the GeoCF a priori. And then on the top, in red, is the actual GeoCF a priori column. So here what we're trying to look at is how much of the diurnal variation is associated with the radiances that tempo measures and how much is associated with the a priori information. What you can see is that, for example, in Chicago, there's this significant ramp up in the column at 22Z, so that's the afternoon rush hour as modeled within GeoCF, and that there is a slight uptick in tempo, but it's nowhere near as large. And there's an uptick in our WRF-Chem at that time period, and we're using a completely different set of emission inventories. So one thing I can say, first of all, that the diurnal variation of the column in New York City from this analysis is fairly small. We're not seeing a whole lot. And it tracks our diurnal column with, we're upscaling a 1 kilometer emission inventory for our 4 kilometer runs. It tracks our predictions pretty well. And it's quite different than the a priori. Same kind of thing for Chicago. Chicago now shows, the GeoCF shows a morning rush hour signature, less so of an evening one. And again, we're systematically higher than tempo, as we saw in the scatter plots, and tempo itself is quite flat. Between the top and the bottom, it's the same kind of thing. The variance is much less, and the overall column amounts are lower. That's its ability to distinguish between urban core and suburban regions, which was one of the milestones for the validation. And here, again, both the GeoCF and our model are slightly higher in New York. Our model is quite comparable in Chicago in the western suburbs. So that's the comparison of the columns. Now I'm looking at some of the other variables, kind of at the request of the tempo SAO, the algorithm leads. So this is looking at cloud fraction over the course of this time period. In the top, again, city core, and the bottom is the suburban region, and it's just the measurements themselves. Remember, we had a cloud fraction criteria had to be less than 0.15. What you see here is that there are never cloud fractions. The mean cloud fractions are always around 0.1 or so. This is a known artifact in the tempo retrieval right now, and sorting out why there's this systematic floor in cloud fraction is one of the things that the validation team is focusing on trying to understand, because that's not realistic. And it also says to the users of tempo data, if we use a typical like 30% cloud radiance fraction, like we use for tropomy, then you introduce a lot of noise. So the recommendation is to use a 0.15 cloud fraction, but you're getting very close to, if you go below 0.1, you're not going to have any data that's being retrieved. So this is a very narrow, right now with this beta release, until this bias in the cloud fraction is identified, there's this very narrow range where you should be looking at the tempo data. This is now air mass factor. Again, just looking for features that would lead to artificial enhancements in the retrieval, either at sunrise or sunset. Air mass factors above or below 1 will tend to damp or amplify the signal, the retrieve column. And again, I put these in as extra slides because I really am still trying to understand them. I don't see a whole lot of variation in the air mass factor, and I don't see a real coherent difference between the Connecticut coast and the suburban and the urban areas. So don't see anything glaringly wrong with the air mass factor either, though. But and I think that is my last slide. So I'll take any questions.
Thank you for the presentation. We can start with questions in the room, but I also want to remind people watching online, if you have questions, please type your question under in the box under the video, and we will read that from the screen. So, any question in the room? Yes.
Thanks, Brad. That was nice. I just wondered, with this, you're looking at an hourly, a monthly mean in the for the data.
Yeah, I'm looking at 11 days.
Sorry?
I'm looking at 11 days.
11 days.
Yeah.
I just wondered if you looked at the daily data. I've just kind of noticed, especially looking at GEMS data, when you do a lot of time averaging or whatever, there are day-by-day differences driven by, could be meteorology, probably less so day-by-day emission changes, but meteorology especially.
Yeah.
But it tends to wash out a lot of the variability you do see. I just wondered, maybe looking at some of this, the monthly average or the individual days could just give a bit more information on the diurnal variation.
Yeah, I think, like I say, I'm looking for directions to go with this part of it. I think, I do have, so I've got all the data, I can choose, it may also be that I'm not really defining these urban cores exactly right, but I could easily, I have the data so I could look at a time series, of the data, and then look at the variance within a small box, spatial box, and see how much day-to-day variability is in the column. And maybe you're right, maybe then more of a diurnal cycle will pop out. That's a good suggestion. I'll do that when I get home.
So a hand. Oh, yeah.
Hi, Brad. Thank you. Is the indirect validation that you found between WRF-Chem and Tempo the same as Tempo and Pandora? I forgot.
I believe that the overall results for Pandora for NO2 are that Tempo is a bit low. I don't recall what it is for formaldehyde. Do you remember? No. So again, the formaldehyde, the model's quite high. So we've got a large bias. And there's a reason that the GCAS formaldehyde retrieval is not ready yet. It's a more difficult retrieval. And as you know, there's even the Pandora formaldehyde has not really been validated. So, but the NO2 results are consistent with the Pandora over a much longer period of time and quite a few other different sites. What was your, you weren't able to do NO2.
No, I
But-
was focusing on formaldehyde
Formaldehyde.
and using the FTIR
Right.
first to compare with Pandora and then compare
Right.
the FTIR with Tempo. And we see I think the same as you in the sense that Tempo was lower than the FTIR.
Okay.
And when I compare Pandora with the FTIR, I see the same. The Pandora is lower than the
Then
FTIR.
FTIR.
But we are limited to 3 sites. But all the 3 sites, one in Mexico City, one here, and one in Canada, are consistent. Like you mentioned, like it's kind of nice to see the comparison with the formaldehyde
Right.
Pandora because they don't know how good it is, or
Right.
I don't know. But
So-
there are way more Pandoras than FTIRs. That's
Right. But even, again, it would, so first of all, the Tempo is a cost-capped Earth Venture instrument mission, which means that there is no funding for Tempo validation. The Tempo validation is being done out of the goodness of people's hearts because they care about the instrument. So I would say, for example, here, if AEROMMA is doing flights out of RAF, make sure that as part of every flight plan, you do a spiral over this building so that you can get profiles so that you can, I'm serious. It should be a part of every single flight so that you can get in situ profiles of NO2 and formaldehyde so we can validate the measurements we're using to validate the satellite.
Yeah, in fact, last week the NOAA guys, I
Yes,
think they were flying over here,
okay.
and I was in contact with them to make sure that they have flights over.
Did they do spirals?
I don't know if they had the spirals.
Yeah. It took quite a bit of effort to get the spirals for the DC-8 into their flight plans. So, but,
Yeah, thanks, Brad. That was great. So do you know if anyone is doing the same with HIQ and GEMS?
no, not that I'm aware of.
Okay. But you think this same analysis can be applied there, right?
Absolutely, yep.
Thanks.
Thanks for the seminar. Yeah, this diurnal profile I'm surprised to see these diurnal profiles. So when I looked at GEMS NO2, I see usually morning to afternoon drop something like 20% to 40%
Yeah.
compared to the morning 9 a.m. data.
Yeah,
So it's all monotone. So
yeah.
yeah. So did you have chance to look at GCAS NO2 column data? I guess they apply morning, noon,
They
afternoon.
have 3 flights per day.
Right. So
I haven't looked at, I haven't looked at the means of that, no.
yeah. Also, model results are also constant
flat.
all over the time. So
What?
curious.
Well, this, our surface NO2 is varying like crazy, but the column's not. So,
Okay.
and we're, if I look at, formaldehyde is a good tracer of the PBL depth. We're getting the PBL very, very well. So
Okay.
again,
yeah.
thanks to all the insight from Gabby in setting up the WRF configuration.
Yeah, might be good to check if these calculations are correct.
Well, you're right, but I make mistakes, that's for sure. As
Yeah.
far as I know, they're correct.
But if this is true, then this means something also,
Right.
right? There's a lot of emissions during daytime. This means.
Or it's just that the variations, I mean, it comes down to, you have lots of variations in surface NO2. And NO2 dies off very rapidly with altitude, but you have lots of variations in the planetary boundary layer depth that compensate, that mask a lot of those changes.
Okay, thank you.
Maybe just a quick follow-up, really nice analysis. Have you looked at WRF-Chem at the vertical variability? I mean, at the different vertical levels and see where you see a lot of the variability during these hours or something? Is it also in WRF-Chem all controlled by what's happening at the surface? Or is there during the day at some point some transport coming in from somewhere or some recirculation going on or just something like that?
I could probably, I mean, I have all the WRF-Chem profiles. I probably could, I mean, I can easily just do, look at the WRF-Chem variability at points, but I could look at the WRF-Chem vertical profiles with this data set and aggregate it in the same way. Yeah, these are good suggestions.
All right.
As I say, I put these as extra slides because I'm still trying to sort them out. I don't think I have a bug, but.
Maybe just for clarification, just came to my head. So you say you take 11 days, then you filter that for clouds, right? So now,
Yep.
do you have kind of an even number of data points for each hour, and do they all represent the same day? Because if not, I can imagine.
Yeah, I haven't looked into how uniform the sampling is.
Right,
at all.
because you might have for 9 a.m. on one day, then you might
Yeah.
have 10 a.m. on another day,
Yeah.
and I mean, it goes back to David's
I think
suggestion on looking at
the raw
individual
time
days.
series would be,
Because you might have
Maximize
one
it.
windy day in there that screws your entire statistics up or something like that.
yeah.
Sort of, is this on? I guess it is. Related to that, you were saying you showed how it was a very smoke-influenced year.
Yeah.
How influenced were these days by smoke, and was it uniformly influenced, or did you select days that were less influenced?
No, I took every single possible, tempo overpass that I could take, and I haven't sorted it by smoke. And so I think the preliminary analysis is there's not a lot of NO2 enhancement because of the smoke. We haven't looked into whether there's a lot of pan signatures and some, thermal decomposition of pan, but we've looked at runs, our early runs, where we weren't trying to refine the smoke prediction, and the later ones, we don't see much difference. But on the tempo retrieval side, if they're smoky days, they don't explicitly account for aerosols in their retrieval. They're kind of treated as clouds. And so smoke could impact the tempo retrieval.
Thanks for your talk. Could you talk a little bit more about the uncertainty due to the GOCF a priori and air mass factor? Is there any plan to, create a different retrieval using a different model, especially since you're using WRF-Chem?
So that we've talked about that. To me, you can take. There's all sorts of papers where you take tropomi or you take OMI retrievals and you put in a higher resolution a priori, and you get higher urban columns and you get more structure. It's all just model results. It doesn't. I kind of shy away from that. Clearly, the quarter. If you were saying I want to look at tempo in a specific urban area, and you have a higher resolution a priori, then that's probably justified to try and do that. As I said, the GCAS retrieval that's publicly available has both the GeoCF a priori and our 4-kilometer WRF a priori. So you can, right now, you can look at the impact of that different a priori on the GCAS retrieval. But here's a day. This is first light, so this is a day that I've been looking at a lot. You see that that tempo shows enhancement all over Lake Michigan, whereas the model's showing a very narrow plume on the western shore. This was an ozone exceedance day on the western shore of Lake Michigan. So to me, this what WRF is showing, these enhancements near the shoreline that lead to convergence and ozone production that we saw, was observed, is a clearer picture. I think there is a lot of spreading of the Chicago plume in the 25-kilometer GeoCF. You can kind of see that. This is the same day. Yeah, does the top one say? Yeah, it does have. These are both, this is GCAS on the top, on Chicago on the left-hand side, and WRF on the bottom. This is a little earlier, it's before when I was showing the tempo one. But GCAS also shows this enhancement over the whole lake. So, but this is using our WRF-Chem air mass factor for both of them. So there are, there's impacts of the air mass factor that the coarse resolution of that are in the data. And so people should be aware of that. Look at these other areas and, we're capturing the plume structure pretty well, so.
Okay, any more questions? If not, this concludes today's seminar. Thank you, Brad, for the talk again.
I have a
thank you all
noon
for
telecon
joining.
I have to get to. Thank you. So thank you for not asking any more questions.
We'll see you all next week.